Hello, I'm Seema and welcome to part 20 of the chapter Alcohols, Phenols and Ethers. In the previous few videos, we have been discussing the chemical reactions of alcohols and phenols, or chemical properties of alcohols and phenols. We studied the first category of reactions where we said that the bond between, which involved reactions that involved the breaking of bond between oxygen and hydrogen in alcohols and phenols. So it was only hydrogen that was leaving and causing the addition of something else. So only where we had esterification. So only hydrogen, the bond between oxygen and hydrogen was breaking. In this video, or from this video onwards in the consecutive videos, we are going to be studying reactions that involve the cleavage of carbon and oxygen bond. So these would be reactions that involve the breaking of the carbon and oxygen bond. Now it is important to remember that in the case of O and H, it was identical. This bond was identical both in phenols and alcohols. But this bond between carbon and oxygen is not the same as in alcohols, is not the same as it is in phenols. Why? Because the carbon in both alcohols and phenols differs in its hybridization. In alcohols, this carbon is sp3 hybridized. So you see 1, 2, 3. It is forming 3 separate bonds, or rather 4 separate bonds with 4 different entities. It could be atoms or groups of atoms like you have methyl groups, but every carbon is attached to 4 other atoms. But in the case of phenol, the carbon is sp2 hybridized and it is attached to only 3 other atoms, that is one of which is O, and the other 2 are the 2 carbons of the benzene ring. And we know that it has got alternating double bonds, and these double bonds participate in resonance in the benzene ring. These are things that you already know. So this carbon has, since it is sp2 hybridized, it forms shorter bonds. Due to resonance, it is more stable. Therefore, it does not allow the breaking, or changes are not that easy. So this kind of reaction, which involves the breaking of carbon and oxygen bond, is not shown by phenols because of its sp2 hybridized character. Because of the resonance, phenols do not show this kind of a cleavage of bond. So in other words, this category of reactions that we are going to be studying are only going to be reactions of alcohols. And under this category, we'll be studying 4 different types of reactions. But before I come to the 4 types, let me just tell you that phenols only show a breaking of carbon-oxygen bond when it reacts with zinc. But we do not include that here. We are now going to study the 4 types of reactions shown by alcohols which involve the cleavage of the carbon and oxygen bond. The first is the reaction of alcohols with hydrogen halides. The second is reaction of alcohols with phosphorus trihalides. These 2 we'll be covering in today's video. And after this, there would be dehydration and oxidation. 2 more categories of reactions which we will be doing in the consecutive videos. So let us start with our explanation of reaction of alcohols with hydrogen halides. Now, this is something that you have already done in chapter 10. A little bit has been explained, but we are going to expand on it. And in chapter 10, on page number 286 of your NCERT textbook, you will find this reaction. Anyway, not wasting any time, let us move on with the actual explanation, what the reaction is and what the mechanism is. The basic reaction is that when alcohols react with hydrogen halides, X is any halogen, it results in the formation of the alkyl halide or the haloalkane and water. So what is happening here? OH, the bond between carbon and oxygen, is breaking. The hydrogen bond between hydrogen and the halogen is breaking. The OH combines with hydrogen to form water, H2O, H, HO. So H2O is formed from the OH hydroxyl group of the alcohol and hydrogen of the alkyl hydrogen halide, and the halogen takes the place of the OH group. So the bond between R and O, that is C and O, is breaking, and it results in the formation of a halide. So this is the basic general reaction that takes place. But we have found that the reaction between the same reaction, if it is a primary alcohol, it shows a difference. There's a difference in the mechanism of the reaction. The overall reaction may be the same, but there is a difference in the mechanisms of the reaction. And there is a test that we use to identify the alcohols, whether it is a primary alcohol, secondary alcohol, or a tertiary alcohol, which is based on this difference. So it is important to now understand how this reaction takes place. So in the first case, I've taken a tertiary alcohol. In a tertiary alcohol, if you see carbon, tertiary means the carbon which is attached to the hydroxyl group is attached to 3 other carbons. Tertiary, 3. So it is attached to 3 other carbons. So this is a tertiary alcohol. So what happens when tertiary alcohol reacts with HCl? The bond between carbon and oxygen has to break. So what happens in the first step is that the lone pair of electrons which is present on oxygen, the first thing that happens, the lone pair which is present goes to hydrogen. And the bond between hydrogen and chlorine, the electron that belonged to hydrogen, it moves to chlorine. Chlorine is more electronegative. It pulls that electron towards itself. And when that happens, chlorine has 7 electrons of its own. Chlorine is a halogen. So it has 7 electrons and 1 electron is of hydrogen in HCl. When hydrogen loses that electron to chlorine, chlorine has 7 of its own electrons and 1 more electron, which makes it Cl negative. So a chloride ion is formed. One thing. The second thing is the pair of electrons on oxygen are given to hydrogen. So what happens? This pair of electrons is used to form a bond with hydrogen. Since hydrogen lost its own electron, it does not have any electron. So this is a coordinate bond. A coordinate bond is when one atom supplies both the electrons in the formation of a covalent bond. A simple covalent bond is where there are 2 atoms, both of them are contributing 1 electron each and they are sharing that pair of electrons. And the bond is a covalent bond. But when the pair of electrons is supplied by one atom and that pair is now forming the bond, it means that this atom is losing 1 electron because it is giving that 1 electron to hydrogen so that it can form the bond. But oxygen becomes deficient in an electron in this process. So the bond is formed. So what do we see? CH3, CH3, this is the same as that. O, the hydrogen is already there and one lone pair which was used is used to form a bond with another hydrogen. That is this hydrogen. But as a result of which oxygen acquires a positive charge because both the lone pair of electrons on oxygen was used up to form the bond with this hydrogen which did not have any electrons. So it results in the formation of this cation. And the anion that is formed is the chloride ion. So this was the first step, that a kind of a water molecule is, you can see here, there is a water molecule that is, you can easily see that H2O would be a water molecule and there's a positive charge, which means that this is not going to be a very stable species. So what happens in the next step is that the next step is a slow step. In this, the water molecule separates. The bond between carbon and oxygen breaks. It is the slow step, and you know that any step that is slow is also the rate determining step. So why is it the rate determining step? You are a group of friends who are walking together. So when you reach, let us say you're doing a 2 kilometer or 2 mile walk. That friend who walks the slowest will determine at what time will you reach your end point. If you're all walking together, the speed of the slowest person determines the speed of how fast would all of you get to the end point. It is the same thing. In a chemical reaction, the slowest step determines what will be the rate of the reaction. Other steps are fast, they are quick. So how long would it take does not actually depend on them because they are quickly finishing their job. But the one which is the slowest will determine how long actually would it take for the reaction to take place. So this step is slow. It is the rate determining step in which the cleavage takes place between the carbon and oxygen. This is the bond that cleaves. Cleavage is breaking. Alright, so this is the bond that cuts. So carbon and oxygen, that is the bond that breaks. Now when this bond breaks, what is happening? Oxygen is positively charged and it does not stay happy, it is unstable, and but oxygen is a very electronegative element in comparison to carbon. So this bond, which has one electron contributed by carbon and one electron contributed by oxygen, this bond, the carbon, since it is less electronegative or it is more electropositive in comparison to oxygen, decides to lose its electron. It loses its electron and therefore carbon becomes positively charged, while this oxygen gets back both the electrons, and that lone pair, its supply is now complete and it becomes neutral. So every oxygen, you know, has 6 electrons in its outermost shell. So it has 1, 2, 3, 4, 5, 6. It gets back its 6 electrons and it becomes neutral. So there is no positive charge on oxygen and you get water. At the same time, you get a carbocation here. A carbocation is a cation in which the positive charge is on the carbon. Now, this is a tertiary carbocation because it was a tertiary alcohol, which means the carbon which has positive charge is attached to 3 other carbon atoms. Now, since it is attached to carbon atoms, alkyl groups, methyl, ethyl, propyl, whatever, all alkyl groups are electron releasing groups or electron donating groups or electron repelling groups. So all of these, they push their electrons towards this carbon because it is positively charged. So they kind of push electrons towards the positive charge. And thereby the need of electrons for this carbon decreases because it is getting the negative charge from the 3 methyl groups. So this carbocation is stable. It becomes stable, and anything that results in a stable product, that reaction is always favored. So you get a stable carbocation. Now in the next step, even if it is a stable carbocation, in the next step it is still a cation, so it has to neutralize itself. How will it neutralize itself? What is the negative species in the reaction mixture? The chloride ion. So in the next step, the chloride ion and the carbon here, it loses a pair of electrons it uses to form a bond. When it uses a pair of electrons, it means that it keeps one electron with itself to form the bond, and one electron it gives to carbon. Therefore, this results in the formation of a bond between carbon and chlorine. Chlorine here in Cl negative has 8 electrons. It is a halogen. It should have 7 electrons in its outermost shell. In this structure, it has 7 electrons. 1, 2, 3, 4, 5, 6, 7, and 1 it has given to carbon. And since it gave that 1 electron to carbon, chloride had 1 extra electron, it loses the negative charge, and carbon had 1 less electron, so it gets that electron and therefore it loses the positive charge and it becomes a neutral molecule, which is the final product. That is the alkyl halide. So this is what happens in a tertiary alcohol. Now I know that I have written these two and I have not explained these. I'll explain this part when I do the Lucas reagent test. But basically, this is what is happening in the case of a tertiary alcohol. Secondary alcohols also follow this mechanism. The only difference is that a secondary carbocation will be a little less stable than a tertiary carbocation. Alright? So you can imagine, you can change any one of these with hydrogen and you can understand it in the same mechanism. Only one of these methyl groups which is attached is only a hydrogen, so it becomes a secondary alcohol. The third example would be here, which is a primary alcohol. And the reason that I did not write secondary alcohol is because it follows the same mechanism. If we imagine that a primary alcohol is also following the same mechanism, let us first make it follow the same mechanism, because theoretically it pretty much can follow this mechanism because these methyl groups are not actually involved in the reaction. So what would you expect? CH3CH2OH plus HBr should give you CH3CH2Br plus H2O, the same reaction. And let us imagine what happens. The same thing happens, that the HBr breaks. Bromine gets this, the 2 electrons of the bond. So the bromine has 1 electron of its own, and the electron of hydrogen is given to bromine. So it results in the formation of bromide ion. I should have written bromide ion here. Plus Br with 8 electrons and negative charge. Okay, so it forms the bromide ion. And what about this part? The hydrogen, it comes here, you know, the same thing. The hydrogen comes here and forms this structure. So you'll get CH3CH2O, and the pair of electrons on oxygen is used to form the bond with hydrogen, which does not have any electron. Therefore, oxygen becomes positively charged and you get OHH, that is H2O is formed. Alright, understandable? In the next step, you expect the same mechanism. That what is happening, that CH3CH2, this is the water molecule which has to be removed. So now the bond between carbon and oxygen should break. So the bond between carbon and oxygen should break to give you the carbocation and water molecule. Just as we got the tertiary carbocation here and water. Now the problem with, even with secondary carbocation, it will be formed, it will be less stable. But a primary carbocation, the methyl group, although it is electron releasing, it does not release enough electrons, or is not that electron repelling that it can stabilize the positive charge. So a primary carbocation is extremely unstable. Since it is extremely unstable, this reaction does not take place with this mechanism. You know, if you are asked to go on a hike, there is one trail which is safer. You're away from the cliff and you're walking safely. You're not a hiker, you're not a natural hiker. So, and there is another a person who it may be easy for him to hike on the edge, or even use those, you know, hiking tools and climb up, do a vertical climb. But since you are not a hiker, you would like to be safe. You would not put yourself in that unstable condition. The same thing happens, that such an unstable product is being, or intermediate is being formed. The intermediate here, the tertiary carbocation, was formed because, although it is an intermediate, it was pretty stable. So the reaction was favored in this direction. Here, the reaction is not favored. So I put a cross here. That this is what we would expect, but this is not what happens. What happens is that the removal of water molecule and the addition of bromine, both these reactions take place in one step. They don't take place in 2 separate steps. And since both the reactions are taking place simultaneously, this reaction, obviously this equation or this step will be very slow. It will be slower than the rate determining step here. Because in this there was only 1 molecule involved. Here there are 2 molecules involved. So it is called a bimolecular step. So it is a rate determining bimolecular step. So it is very, very slow. So what happens? But at least it is happening. Here this is so unstable that this reaction is not going to follow this route. The route it is going to follow is a bimolecular reaction. So in this you have water molecule, the bond breaks, the electron goes to oxygen. Oxygen has 1 electron of its own, and the electron of carbon goes to oxygen, so the positive charge is lost. Since the bond has broken, you now have water. Alright? And at the same time, the Br negative that is present comes and attacks this carbon, which had acquired, which kind of becomes positively charged because it lost its electron. And that electron, that extra electron that it has, it uses a pair of electrons to form CH3CH2 Br, to form a bond between this carbon and bromine. So you get the primary alkyl halide. Right? So basically, why do I explain that? The reaction is the same. If you see that ROH and HX is going to give you RX and H2O. The same reaction has taken place, only the mechanism is different. So why do we need to understand the mechanism? Because there is a chemical test that we carry out in the laboratory. The difference in the reactivity of the three classes of alcohols with hydrogen chloride, the difference in the reactivity. Here I took HBr, you could have taken HCl. If you took the same chemical, that is HCl, HCl, if you form the chloride, the difference in the reactivity with the same reactants is different in the case of primary, secondary and tertiary. And the rate of the difference in the reactivity of the three classes of alcohols with hydrogen chloride distinguishes them from one another. So there's a reagent that is prepared in the laboratory. It is known as Lucas reagent. Lucas reagent is nothing but a mixture of concentrated hydrogen chloride and zinc chloride. So if you wanted to see the Lucas test, instead of this bromine, if I put chlorine here, chlorine, this would also be chlorine then. This would be chlorine, because Lucas test would be where we'll be carrying out the test with chlorine, HCl, Cl, and this also becomes Cl, right? So what happens? Lucas reagent is a mixture of concentrated HCl and ZnCl2. As I showed you here, that it is HCl which is being used in every reaction. The ZnCl2 in the case of tertiary alcohols is not even used. But I'll explain. I told you that the tertiary, the carbocation is so stable that this reaction is favored and it automatically follows with hydrogen chloride. It automatically follows this mechanism, and since this is a single molecule rate determining step, this is a faster reaction. It is really fast. It is so fast that in Lucas reagent, zinc chloride is used as a catalyst. It helps in this reaction. In the case of tertiary alcohol, zinc chloride is not even required. It will show its reaction with hydrogen chloride without the help of a catalyst. In secondary alcohols and primary alcohols, ZnCl2 is used as a catalyst. When we put Lucas reagent, you have ZnCl2, which is a catalyst, zinc chloride. And concentrated HCl, of course, is there. So as I told you, that this is so reactive that it does not even need zinc chloride, but it will immediately react with hydrogen chloride. This would react with hydrogen chloride with the help of would react with HCl with the help of zinc chloride, yet it will be the slowest reaction. And the secondary alcohol would be in between these two. Now what happens as a result of this? I'm sorry, I had to leave, but where were we? So yeah, I was talking to you about the Lucas test, that we take hydrogen chloride and zinc chloride and we carry out the same reaction, and we carry out the reaction of alcohol with HCl to produce the halide. So let us see what happens. According to the speed of the reaction, I just explained to you that tertiary alcohols would be the fastest and they do not even need zinc chloride, which is a catalyst, and they'll show this reaction. The second thing is the secondary will be slower and primary would be the slowest. So alcohols are soluble in Lucas reagent. If you take alcohols and you dissolve them in Lucas reagent, they will dissolve. That is concentrated HCl and zinc chloride, while their halides are insoluble. So we know as soon as you put the alcohol in HCl and ZnCl2, it is going to react with the HCl. And it is going to result in the formation of the halide. But the halide will be formed the fastest in the case of a tertiary alcohol, slightly slower in secondary alcohol, and the slowest in a primary alcohol. So while their halides are insoluble and produce turbidity. Turbidity means a milkiness, that is, the solution becomes unclear. So I just got some water here in a cup. So this is the water that is clear, and it's absolutely clear. So initially when you take Lucas reagent, HCl and ZnCl2, it is, or the alcohol, it is absolutely clear. But as soon as you add the alcohol to it, or if it is, let us say this is Lucas reagent and you're adding the alcohol to it, if you add a tertiary alcohol, immediately it turns milky or it becomes turbid, right? So you observe a turbidity that is formed in the solution. That is, the solution does not remain clear. A turbidity is produced. And tell me, what will happen in the case of secondary alcohol? What will happen in the case of primary alcohol? The reaction in primary alcohol is the slowest because this is a bimolecular rate determining step. It is much slower than the tertiary alcohol. Tertiary alcohol did not even need the catalyst to carry out this reaction. But the presence of the catalyst in Lucas reagent is going to make it even faster. The reaction even faster. So as soon as tertiary alcohol is put into the mixture, it immediately turns turbid. The solution becomes turbid because the halide is formed, the tertiary halide is formed, and therefore it turns turbid. A secondary alcohol will take slightly longer. The turbidity will be produced, but it will take, you will mix them and then you'll wait a little and you'll see slowly turbidity being formed. But a primary alcohol, you'll keep waiting and still there will be no turbidity. It is such a slow reaction. So we say that while their halides are insoluble, since they are insoluble, they will produce the turbidity. Tertiary alcohols, turbidity is produced immediately. In the case of secondary alcohols, turbidity is produced with less ease, it takes longer, and with primary alcohol, there is no turbidity at room temperature. At room temperature, the reaction will not take place. But if you heat up the test tube or the cup or whatever container you have, let us say I had a beaker, you warm it up, then the turbidity will be visible. Otherwise, it will appear to be plain clear. That shows the difference in the rate of reactions, on the basis of which we can tell, okay, turbidity was produced immediately, it means this must be a tertiary alcohol. Turbidity took a little bit of time, it must be a secondary alcohol. There was no turbidity at room temperature, I had to warm it up, now I see turbidity, it means it is primary alcohol. So the Lucas reagent test is used to distinguish between primary, secondary and tertiary alcohols. In the laboratory, when we do the organic analysis, once you know you've got alcohol, you would like to know what alcohol, which type of alcohol is it? Is it primary, is it secondary, or is it tertiary? So that differentiation is done with the help of the Lucas test, and that is the reason why I explained the entire mechanisms to you. The second category of reaction doesn't need any explanation, I'm only going to explain what happens, is the reaction with phosphorus trihalides. This reaction, where alcohols react with phosphorus trihalides to give the alkyl halide, is also given on page 286 of your NCERT textbook. It is in the same category of few reactions that are given. So alcohols react with phosphorus trihalides to give the alkyl halide, and phosphorus acid is produced, H3PO3. So ROH plus PBr3 will give you the alkyl bromide and H3PO3. So you can get the alkyl halides either with alcohols, reacting alcohols with hydrogen acids or hydrogen halides, or you can get it through phosphorus trihalides. So these were two reactions, and we will continue with our discussion of reactions which involve the cleavage of CO bond in the next video. So if you wish to watch the other videos of this chapter, please click the link that will appear on top of the video. If you found this video helpful, give it a thumbs up. Please subscribe to my channel. Increase, your likes and your subscriptions help YouTube to suggest my videos to other children. And it would really help if I can reach as many children and they can benefit from this effort that I am making. So if you found this video helpful, give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.